All right, in this and in the next few videos, we're going to talk about chapter 5, which is about mechanical vibrations or spring and mass systems. And the basic setup is the following. So suppose you have a box, and what this box is here is I have kind of half the box cut out so you can kind of view in the box. And what you have in the box is you have this mass M. So maybe it's just a ball or a marble, whatever, it doesn't matter. We're going to ignore friction for now. So just imagine that it's in the box, it's on a frictionless bottom, and it's attached to one wall by a spring. So there's the spring that's attached to it, and the spring, you can stretch it, in which case the mass would be further from the wall where it's anchored, farther from the wall where it's anchored, or you could compress the string, in which case it would be closer. You could also assume that on the other side of the mass, there's kind of a what's called a dash pot or a dampener. And the idea is that can like take away some of the vibrations and it can change the way that the system works. So this thing over here is called a dash pot. Okay. And so what we're going to do is we're going to study what happens if you take this object and then stretch it and then let go under different circumstances. Would it just oscillate back and forth infinitely far? Would it settle down? And so on. So again, x equals 0 is going to be the equilibrium point. So it's the point where you would just let go and nothing happens. So it just doesn't move. If x is positive, that means that the string is going to be stretched. And if x is negative, then the string is compressed. Okay, so it's closer to the wall than the equilibrium position. And there's a few things that are going to help us out here. The first thing is Hooke's law. Okay, so Hooke's law says that if you look at the resistive force for how this object is gonna react, that's going to be inversely proportional to where x is. So what this means is that if x is at the equilibrium position, there's no force at all. And if x is positive, what's going to happen is the object is going to move in the negative direction, and it'll move proportional to x. So if you were to have x, say 1 unit stretched, that's going to move at a certain rate. And if you were to double it, it would move at double that rate back towards the equilibrium. So that's Hooke's law. So this is the resistive force, and that's proportional, inversely proportional to x. You can also assume that the dash pot, the dampener, is going to have, so I'm going to call this F sub D for dampening. So we're going to assume that that's proportional to the velocity. Okay, so that's the force that's going to be acted on by the dash pot. So that force is going to be proportional to the velocity that the mass is moving. And so here, K is positive, K is the spring constant. C is positive, C is called, so C is called the dampening constant. So the dampening constant. Okay, and let's let F sub E be any external force whatsoever. Okay, so Fe is any external force. Okay, so anything that we haven't quite considered yet. And then it turns out that the sum of the forces, so we're going to have the resistive force from Hooke's law, we'll have the dampening force from the dash pot, plus maybe some external force. Let's say F of E, let's just call this capital F of T. And we know that F equals ma. Okay, so Newton's laws tells us that F equals ma. So this tells us that ma is equal to negative kx plus cv plus F of t. And in other words, what just happened is here a is the acceleration, so that's x double prime. V is the velocity, so that's x prime. So this tells us that mx double prime minus cx prime plus kx equals capital F of t. And all of a sudden we have a second order linear, non-homogeneous, possibly non-homogeneous second order linear ODE. Okay, so there's so many words I forgot them, but it's second order, it's linear, it's non-homogeneous. Okay, constant coefficients. Now, if you don't like the setup where you have a box and you have to ignore friction, just turn the box on its side so that the mass is hanging. And then this becomes a little bit more realistic of a model. I'm still going to go back and think about, I think it's slightly easier to think about the model where it's just in the box and you could ignore gravity. But if you want this to be a little bit more realistic, turn it on its side and then the mass is allowed to move up and down. Again, when the spring is stretched, so when the spring is stretched, we're going to let x be positive. When the spring is compressed, x will be negative. Okay, but otherwise we get basically the same equations. And what we're going to have to do is, in all cases, we're going to look at solving this set of equations. Okay, so that's what we're going to do in the next set of videos.